Good day everyone, I'm CJ Webster, inventor of the Polycode, and in this video I'll be illustrating how the Polycode securely stitches together physical workflow processes with states of a process log, achieving integrity of a supply chain, manufacturing process, or distribution network. The Polycode has four basic elements. The main string of polydigital numbers that is encoded resides within the code cells, which are a majority of the colored cells visible. As an internal integrity check, the code also contains a small number of validation cells. The code can only be properly interpreted in one orientation, so there are also a small number of orientation cells, which also serve to encode certain pieces of critical information as per the user's choice. Finally, the Polycode can look like almost anything, and so the shape and pixel count serve as a filter by only allowing authorized user devices to even read a given code in the first place. A hashing algorithm is basically a complicated math problem that computers can run quickly and easily in one direction, but cannot run in reverse to figure out the input. They are useful in giving solutions to these math problems that appear random, but importantly, are predictable in the forward direction. Any organization using the Polycode technology will use the Polycode core software and its hashing algorithm. The using organization will be able to choose or create one or more hashing algorithms for their own use, as well as the particular shape and pixel count to use. One of these hashing algorithms will also be used in producing the map associating certain critical states with certain orientation schemas. I'll explain this more in a bit, just keep in mind that like any hash function, this map is one way. For any critical state of interest, it's easy to calculate the resulting orientation schema, but given a particular schema, the input critical state information is unknowable. In the first workflow step, a particular real physical asset is recognized as entering the system. This could be one of many supplies in a supply chain, or a raw component at the beginning of a manufacturing process, or a finished good entering a distribution network. In any example, the system recognizes one or more critical states measured along the overall process. This could be an asset's temperature, weight, geolocation, or oftentimes will be the time state, ensuring that assets are moved from stage to stage along the workflow according to time-sensitive requirements. The description of the asset is stored in the user organization's database as the original or root data for that element. The time or other critical state data is stored as well. This root data serves as the input for the first code string, derived by taking the hash of the root data, output as a polydigital string of integers. The critical state data is encoded as a particular orientation schema, derived through the mapping hash algorithm I mentioned on the previous slide. To generate the first polycode, the code cells, which are the visual representation of the polydigital code string, are themselves hashed to derive the validation cells. Adding the orientation cells according to their schema gives the full original polycode. So, this cryptographic barcode serves as a metadata link back to the root data and associated time or other state data if a user is authorized to scan the code and access the organization's database. And as a process integrity check, the particular polycode used is reproducible from the root and state data if a user is authorized to use the algorithms. I'll show this integrity check in a moment, but just keep in mind that there is nothing random or arbitrary about the form this polycode ends up taking. It is the secure, inevitable result of the real-world data used as the input. This input data isn't reverse engineerable from the code, but the correct input is rapidly confirmable into the examined polycode. In a successive workflow stage, the physical asset undergoes some sort of development, whether that be a manufacturing step, an aggregation, transportation, or the like. This stage will have its own time or other critical state, and these two values are stored as data. For this hash calculation, the descriptive data of the stage is hashed with the preceding polycode used as a header, linking the two steps. The critical state data is again encoded in the orientation schema. The new polycode is generated, functioning as a metadata link back to stages A and B, and is now the inevitable result of the two successive workflow stages and the two values for the critical state data. All other successive steps follow the same pattern, forming a chain of securely linked polycodes and input data, ensuring the integrity of the overall process as required by the critical state being tracked. To illustrate how this integrity check works, consider a user scanning the original polycode as part of a quality check. The first thing the user's device does is try to match the code to its one or more onboard defined code shape and pixel counts. This rejects users trying to scan other organizations' codes. If it recognizes the shape and pixel count of the code, it searches for one of its onboard defined orientation schemas. This rejects expired codes or codes with errors. If a valid orientation schema is found, the device next runs the associated validation checksum, and if the code passes as authentic, the device will submit the code string as a metadata link. If an entry exists in the database under that code string, the root data describing the asset is then accessed. The device does not directly know the critical state data, such as the time of this workflow stage, but it knows a defined range of what that data must be if the integrity of the overall process has not been compromised. For example, if the time sensitivity of the process requires that this quality checkpoint be within 5 minutes of the original process, then there are only 5 minutes worth of values in that acceptable scope for stage A. Using this generated acceptable scope of state data, the device can then process the resulting polycode for each. The result will be a collection of every possible polycode which would be the result of an acceptable process. If the polycode scanned by the user matches one of these, then the asset is accepted, and if it is anything else, it is rejected. For successive stages polycodes, the process is the same, except carried over more iterations. Once the range of acceptable stage A polycodes has been processed, these must then serve as the beginning of stage B's algorithm. Using this technology, every asset has a scannable link to each stage of its process journey, and the critical state integrity is cryptographically confirmable for every quality passing asset. Using modern cryptography and the Polycode, this record is irreversible and impossible to reverse engineer, but rapidly confirmable given a valid input. Modern hash-based cryptography has enabled digital records to be as permanent as physical objects. The Polycode enables physical assets to exist as the mathematical result of the underlying data of their workflow.